Last time we talked about systems of linear equations, what a solution consists of, and what it means for a system to be in row echelon form. This time we're going to actually solve a system of linear equations using Gaussian elimination. And the idea behind this is just that if a system is not already in row echelon form, and you can use back substitution, what can we do to put it into row echelon form? Now I know what you're thinking. Isn't this series supposed to be about matrices? Well, as we'll see in this episode, the matrix is the fundamental tool we need to introduce to make solving systems of linear equations easy and quick. What we want to do is find out when two systems of linear equations are equivalent. Equivalent simply means that they have the same solution set. If they look different but have the same solution set, we want to say that they are really the same system in a sense, because all we care about is the solutions. So, for instance, x plus y is equal to 0 and 2x plus 2y equal to 0. These two equations are equivalent because anything that solves the one, any x, y, which solve the one, solve the other as well. So if each of these equations was considered its own system, then these two would be equivalent systems. Alright, so what can we do to systems of equations which will produce equivalent systems of equations so that we can manipulate them a little bit and get them into the form we want? Well, there are exactly three things that we can do. The first is that we can swap or interchange, as we often say, two equations. So as an example, suppose we have the system 2x plus y is equal to 1 and x minus y is equal to negative 3. If this is our system of equations and it has some solution set, then if we were to change the order of these two and we were to say instead our x and y have to satisfy x minus y equals negative 3 and 2x plus y is equal to 1 instead, you can see this is the same thing as this. And in fact, you might be thinking to yourself, okay, since when were we even taking order of equations into account? Does it really matter which one we call equation 1, equation 2, equation 3? And it really doesn't, but it's going to when we introduce matrices. So this is one very nice thing that we can do that does not change the solution set at all. Alright, the second thing we can do, we can multiply an equation by a constant, a non-zero constant, I should say, by non-zero number or constant. So, if we have, we could use the same system of linear equations here. Suppose we were to multiply one of these equations by 3, let's say the bottom one. If we multiply both sides of this by 3, then what do we get? We get 3x minus 3y equals negative 9 instead. We can replace this equation by the new one, which is multiplied by 3, and the system of these two equations is going to have the same set of solutions as these two did originally. And it should be fairly easy to see why. You're doing the same thing to both sides of this one equation, so you have not altered anything fundamentally there. Alright, the third thing that we can do, and this is the one that's not as obvious, is that we can add a multiple of an equation to, I should say, a non-zero multiple. Add a non-zero multiple of an equation to another equation. This one, I will do an example in just a second to show you it really is legitimate. But what I want you to think about with these three operations on our system of linear equations is that all three of these change the face, the form, if you will, of the equations, but they don't change the content. They don't change, they're like information preserving changes. So the fundamentals, namely the solution set, that is the most fundamental property of a system of equations, is its solution set will not change. Okay, now as an example of that third property, let's look at this system of linear equations. I claim that this has solution x equals 1, y equals 0, z equals 2. So let's verify that real quick just to be sure. So we have 1 plus 0 plus 2 is 3. That's correct. Now 2 times 1 is 2, minus 2 is 0, so that one's correct. Now 0 plus 3 times 2 is 0 plus 6 is 6. So this is indeed a solution of this system of linear equations. Now let's add a multiple of a row to another row. In particular, let's add 2 of row 2 into row 1. So let's say, so we're going to have x plus y plus z is equal to 3. And we're going to have 4x minus 2z, we're multiplying this by 2, is equal to 0. Alright, now let's add these sides of the equation and add these sides of the equation to give us a new equation. So we'll get x plus 4x is 5x, y, and there's no y's in the second one, so just plus y, z minus 2z is minus z, and then this is going to be equal to 3 plus 0 is 3. Now the question we have to ask here is, when we added this multiple of the second row into the first row and replaced the first row with that, does it still have the same solution set? So I claim this is still a solution of this equation, and this equation, which would be our new system of linear equations. So we've already verified that 1, 0, 2 is a solution of this and this. So let's just check this last one. So 5 times 1 would be 5, plus 0 for y and minus 2 for z is equal to 5 minus 2 is equal to 3. So we do see that adding a multiple of one row to another row and replacing that other row with the result does give us a system of linear equations which is equivalent to the original. Now we need to make a very key observation, and that is, notice that in every problem, no matter what we call these x1s, x2s, xn's, until the end of the problem, they are essentially placeholders. All that is helpful in determining the solution are these coefficients, right? And the constant terms on the other side. These coefficients and constant terms, the actual concrete numbers of the problem, are what we need in order to distinguish one system of linear equations from another, and which essentially determine the properties of the solution set. So the critical observation is this: we don't really need, so long as we keep things orderly, we don't really need to write these x's in there. Instead, if we want to condense this system down to its essential bare bones information, all we really need are the numbers. And this is the observation that leads us to the concept of a matrix. Alright, now we're ready to talk about matrices. So the definition of a matrix is just a rectangular array of numbers. We usually write it in either square brackets or big parentheses, whatever you prefer. I will probably do both. So it's just a rectangular array of numbers as such, with m rows in general, 1, 2, 3, 4, 5, 6, 7, 8, etc. up to m, and n columns, 1, 2, 3, 4, 5, 6, all the way up to n over here. And a matrix with m rows and n columns is said to have size m by n. Now the key things to see here are the matrix coefficients. So the way we write these subscripts, so a sub ij, the first index represents the row number, and the second one represents the column number. So for instance, if I say A21, this represents the entry in row 2, so down 1, and column 1, so it's just going to be this entry right below A11, A21. Also, our indices here, I and j, are going to range between 1 and m and 1 and n. So 1 is less than or equal to I, is less than or equal to m, and 1 is less than or equal to j, is less than or equal to n. This just is another way of stating the size, right? There are m rows and n columns. Lastly, in the special case where m and n are the same number, which is a case which will come up frequently, we call this a square matrix if m is equal to n. So we have an n by n square matrix, and in which case the entries A11, A22, A33, and so on, all the way up to ANN, we call the main diagonal elements. Now that we have the concept of a matrix, what we can do is use this to represent our system of linear equations. So this is our system, right? We have our coefficients A11 all the way up to A1n, down to AM1 all the way up to AMN, and our constant terms B1 to BM. And this gives rise to two different ways of sort of representing our system. The first is as a coefficient matrix. So coefficient matrix, and it's exactly what it sounds like. It's going to be a matrix with our coefficients. Now, in order to get this correct, what you have to pay attention to is make sure when you write your system of linear equations in this rectangular array first, that you have all your x1s lined up and all your x2s vertically, x3s, x4s, all the way up to xn. And then if you write it this way before you put it into the matrix form, it will be easier for you to do it without making any mistakes. So this is going to give us, and I'm already using the parentheses version, A11, A12, all the way up to A1n, A21, A22, all the way up to A2n, down to AM1, AM2, M2, and all the way over to A sub mn. Again, this is just the m by n matrix of our coefficients, so these a's of our system of linear equations, right? This contains almost all the essential information about the system. I say almost because we need to include these constant terms as well. And this leads us to our second sort of representation of our system of linear equations. This we may play with later, but right now we're going to be using the second way. This is called the augmented matrix of our system of linear equations. Augmented matrix. And it is the same thing as this, but with this column added for your constant terms. So A11 all the way up to A1n, down to AM1 over to AMN, dot dot dot. And then we put this line in, which is called a partition of the matrix. I'll write that, partition. And then we put our B1, B2, etc., all the way up to Bm. And this matrix, the augmented matrix for our system of linear equations, contains all the essential information about it, and this is what we will be using to solve it. Just as we were able to perform 3 different operations on a system of linear equations and get an equivalent system of linear equations, so too can we perform the same essential 3 operations on an augmented matrix which represents a system of linear equations to get an equivalent augmented matrix. Equivalent here meaning represents the same solution set. So what can we do? Well, number 1, we can interchange 2 rows. Instead of equations, we now have rows. Number 2, we can multiply a row instead of an equation by a non-zero constant. And lastly, we can add a multiple of another row, or of a row to another row, right? And that replaces the second row, the one you add to. So as an example, suppose our augmented matrix looks like this, right? This is for a system of two equations and two unknowns. Then equivalent systems would be, let's just change the rows. Well, now we have 1, 1, 2, and 1, 0, 1. These are equivalent systems of linear equations, or at least they represent equivalent systems. We can multiply by a constant that's non-zero. So how about 1, 0, 1? And then for the second row, let's multiply by 3. So we have 3, 3, and 6. These two are equivalent. And these two are equivalent because, well, although we haven't talked about this, if A equals B and B equals C, then A equals C, right? So if these two are equivalent, and these two are equivalent, then these two are equivalent, and so on. Equivalence is an equivalence relation. Although you may not know what an equivalence relation is, but never mind. We can do multiple of these operations if we want. Lastly, we can add a multiple of a row to another row, right? So let's add 2 of row 1 into row 2. So 2 plus 1 is going to be 3. And 0 plus 1 is going to be 1. And 2 times 1 is 2 plus 2 is 4. These two are also equivalent. So these three operations, and as I alluded to before, doing it multiple times is going to be our path to getting a system of linear equations into a form where we can easily solve it. Alright, so our goals in solving a system of linear equations are as follows. 1, to use the augmented matrix of the system to make things more clutter-free and just visually compact. And second, we want to use equivalent systems of linear equations to try and trade our system out for one which is easier to solve. And in particular, we want to get it into row-echelon form as we introduced last time. Now, just as each system corresponds to an augmented matrix, so a system of linear equations in row-echelon form corresponds to the concept of a matrix in row-echelon form. So what is row-echelon form for a matrix? Well, it's a matrix which exactly looks like the following. So there are 3 properties. All rows of zeros are at the bottom. So if you have a row of zeros, it's going to be at the bottom of your matrix like so. Leading entry is the second property. Leading entry of each row is a 1. Leading entry is just the first non-zero entry here. So, etc. So you have first entry in this row is a 1, the first entry in this row. You can have anything you want after that, 296. But the first entry is going to be a 1. And then the last thing is leading entry of a lower row is to the right of higher row. So this is just to say that it does the stair-step pattern like we saw before. We don't see a 1 with a 1 directly below it, but rather there's always a 0 below the 1s, and as you go right, like there could be a 0 here, for instance. We could have 2 zeros, and then so long as this is to the right of this, and this starts with a 1, then we're fine, and it continues like that, and you have the stair-step pattern. So these 3 properties, that all rows of completely zeros, so you have a row of all zeros, are going to be at the bottom of the matrix. The leading entry of each row, the first non-zero entry, is going to be a 1, and it has a stair-step pattern. So underneath each one is all zeros. You see. So this is what it means for a matrix to be in row echelon form. And now we are finally ready to talk about Gaussian elimination. So how do we solve systems of linear equations using Gaussian elimination? It's very simple. First, we write down the augmented matrix for the system. So we write our system of equations out in rectangular form, and then we put the coefficients and the constant terms properly into the augmented matrix as I showed you earlier. Step 2, we use elementary row operations to put augmented matrix into row echelon form. So you'll see how to do this in a second when I do an example, but our goal is just going to be to, as it says, to use a combination, a sequence of these elementary row operations which don't change the solution set to get our augmented matrix into that nice row echelon form that we like. And then last, we just use, we convert it back into our system of linear equations, and we use back substitution, as I showed you last time, to solve the system. And that is solving a system of linear equations. Let's try a couple examples. So first we have this system, x minus y is -1, 3x minus y is 1. First we put it into augmented form to our augmented matrix, so this is going to look like 1 in front of the x, 3 in front of this x, -1 and -1. Then we partition, and our constant terms are -1 and 1. This is our augmented matrix for this system of linear equations. Now we use elementary row operations to get it into row echelon form. So since there's a 3 down here, we're going to want to get rid of that and turn it into a 0. So the first thing we want to do is multiply 3 of row 1, or rather -3 times row 1, and add it to row 2, and replace row 2 with that. So what do we get? Well, row 1 stays the same, and row 2 becomes -3 plus 3 is 0, -3 times -1 is +3, plus -1 is 2, and -3 times -1 is +3, plus 1 is 4. Alright, we're almost there already. All we have to do now is to make sure that this second row has a leading entry of 1. So all we have to do is multiply 1/2 times row 2 and replace row 2 with that. And we are left with 1, -1, -1, 0, 1, and 2. And now, if you'll check, this augmented matrix is in row echelon form. So we can change it back into x's and y's and use back substitution. So let's do that. So let's put this up here. We have x minus y is equal to -1, and we have y is equal to 2. This is a much easier system to solve, right? Because we already know that y is equal to 2 from the second equation. So we have x minus 2 is equal to -1. Equivalently, x is equal to, if we move it to the other side, x is equal to 1. So now we have our solution, x comma y is equal to 1 comma 2. That is our first example. Okay, now for our second example, let's do a case where we have 3 equations and 3 unknowns, which I've labeled x1, x2, x3 here. So we have our 3 equations. First thing we want to do is put this into augmented matrix form, and note that everything isn't written out already in that nice form that we want. So let's do an intermediate step here, which is always helpful, and write it in the form that will not confuse us when we make the augmented matrix. So x1 should be over here. So we have 1 times x1 plus, there is no x2 in this second equation, so 0 times x2 plus 1 times x3 is equal to 3. Then for the last one, similar story, 0 times x1 plus 4 times x2 minus 1 times x3 is equal to -7. And now it's clear what the augmented matrix will be. We'll have 3, 2, -1, -5, 1, 0, 1, 3, and 0, 4, -1, -7. Okay, so we have our augmented matrix. I've rewritten our augmented matrix up here so that we have plenty of room. So now let's use our elementary row operations. Well, the first thing we might want to do is to switch two rows. Let's switch row 1 and row 2 because row 2 already has a 1 in its leading entry. So let's try that. So then we'd have 1, 0, 1, 3, 3, 2, -1, -5, and 0, 4, -1, -7. All right, now let's try adding -3 times row 1 and putting that into, adding that to row 2 and replacing it. So -3 times 1 plus 3 is going to be 0. Then we're going to have -3 times 0 plus 2 is 2. -3 times 1. -3 minus 1 is -4. -3 times 3 is -9. Plus -5 is -14. And 0, 4, and -1 and -7 just as before. Alright, so this is our augmented matrix right now. We're getting close, but we're not quite there. Let's add -2 of row 2 into row 3 to cancel out this 4. So 1, 0, 1, 3, 0, 2, -4, -14, and then this first entry is going to be 0, multiple of 0 plus 0 is 0. -2 times 2 plus 4, it's going to be 0. Then we're going to have -2 times -4 is positive 8. Minus 1 is 7. And then we're going to have -2 times 14. -2 times 14 is going to be positive 28. Minus 7 is going to be positive 21. All right, we're almost there. Let's now turn these two into ones by multiplying those two rows by a constant. So our first row stays the same. And then let's multiply this row by 1/2. So we'll get 1, -2, -7. And then for the third row, let's divide by 7. So 0, 0, 1, and 3. Now if you'll check, this is in row echelon form and we can use back substitution. So if we write this as a system again, we would have x1 plus x3 is equal to 3. x2 minus 2x3 is equal to -7. And x3 is equal to 3. Well, we know already that x3 is equal to 3 because that's what the last one says. Let's plug that into equations 2 and 1. So that's 3, and that's 3. And we see that this is 6, so if we add that to the other side, x2 is going to be equal to -1. And if you subtract 3 from both sides there, we see that x1 is going to be equal to 0. So that our solution to our system of linear equations is going to be 0, -1, 3.